All right, we're about to head into a pretty darn long video. I don't know how long this is going to be because I'm just starting it, but I'll bet if you look at the timeline at the bottom, it's going to be a long one. But realize that's because this is a major, huge subject within calculus. If your parents took calculus and they've forgotten everything about calculus except one thing, this might be that one thing. So I call this curve sketching, but it might be called maximization, minimization. There's other names for it. Let's begin with just a kind of an intuitive idea of what's going on. For this example, I'm going to use a very cooperative function. It doesn't look cooperative, but believe me, it is. So we've got some very curvy function, and we really wouldn't have privilege to see this, but for this case, I'm going to show you that this function looks like that, and we're restricting ourselves to this domain. So the idea what you're going to start learning in calculus is this. This curvy function has regions where it's going uphill, and that's called increasing. Downhill, that's called decreasing. This function has high points and low points. Those are called extrema, or maximums and minimums. And by the way, those can happen at endpoints as well. For example, that's a minimum right there because it's a low point, and that's a maximum. There's a minimum. That looks like a maximum, but by the fine print of the lawyers of math, that's not a maximum because there's no point there. So that's neither a maximum nor a minimum because there's nothing there. And then the lawyers of math would say, well, you can't say that point right before it is a maximum because there's always another point that's one itty bit closer to that. So this is kind of a math black hole. We are also going to talk about concavity, which is the curvature of the graph. In this case, right in this region, this function is concave down because concave down looks like a frown. And in this region, this function is concave up because it's shaped like a smile. And then a point of inflection occurs, I don't know, right about here maybe. And a point of inflection is where you switch from a concave down to a concave up shape. All of these things we see on this graph because I've graphed it for you, but normally you wouldn't have that, and you'd have to just work with this to discover those items. As we're doing this, you're going to learn to make sure that you justify your results AP style so you get full credit for your calculus knowledge. And then in 2 future videos, we're going to add on to this. So look at that. It's taken 3 minutes just to introduce what the heck we're going to do. Let's get to it. As they say in the show Letterkenny, pitter patter, let's get at her. So this is the very first thing you're going to do on any of these problems. It's a knee-jerk reaction. You have to find the critical values of the problem. Well, a critical value, I'm going to give you the actual definition, but it's going to be easier in practice. Critical value are the x-coordinates where your first derivative is 0 or your first derivative is undefined. So our original function was that. So if we're thinking critical values, we have to take the first derivative. Okay, good old power rule. Remember, I've chosen a very cooperative function. And once you take the first derivative, you've got to set up when does my first derivative equal 0? When is my first derivative undefined? So to find out when my first derivative equals 0, in this case, because I've chosen a cooperative function, I can factor it and find out at x equals -3 and x equals 2, this first derivative equals 0. So those have become critical values. I also have to think about when is my first derivative undefined. But this first derivative is very well behaved. It doesn't have any discontinuities or corner points or denominators of 0. So my first derivative becomes undefined never in this case. This is going to happen frequently, so frequently that you're going to be tempted to skip this part of the definition and then they're going to get you. Okay, but anyway, we have found our critical values. That means in the life of this function, x equals -3 and x equals 2 are possibly some exciting times in the life of that function. So the next question is, why did we find those critical values? We find those because we're going to build what I call the first derivative number line. All right, so let's take a look at that thing. This is a brand new concept to you probably. I write down that's a first derivative number line because later on we're going to do a second derivative number line. And I put in the domain, a -4 is where we started, and a 5 soft bracket because we never got to the 5, if you recall. We had that open end point. And our two critical values also get put onto the number line. Reasonably in an accurate place, but it doesn't have to be precise. If I would have had any values here, let's say an x equals 1, then I would have had an x equals 1 on here. So I'm starting to build my first derivative number line by putting on the endpoints and the critical values. And then your next step is going to be to test points in those intervals. And here's what we mean by testing points in those intervals. For example, between -3 and 2, there's a -2, a -1, a 0, a 1, and all those other points in between. I just choose any point in there that I feel like working with. So generally, pick the point that's going to be easiest to work with, and usually x equals 0 is darn easy to work with. And what I do is I take my x equals 0 and I plug it into the first derivative. So my first derivative, if I look back up at the top of the paper, f prime of x was x squared plus x minus 6. So now I plug in a 0, 0 squared plus 0, minus 6 equals -6. Here's what I've discovered. When I plugged a 0 into my first derivative, I got out a -6. All I care about is the plus or minus sign, so I put a minus sign in this interval. Now I tested x equals 0 and I got a negative, but what this is telling me is any x value that I choose within here, if I plugged it into my derivative, I would get out a negative. I just so happen to work with x equals 0. So in here, if I took an x equals 4, because 4 falls in that interval, I plugged it into my first derivative, and take my word for it or do it yourself, I get out a positive value. And over here, this one's a little rougher, but I get out a negative, or I get out another positive value. A little pro tip for you here, when I plug in a -3 1/2, you would say this. How am I going to plug a -3 1/2 into this first derivative? But in this case, if this first derivative were put in factored form, and I plug a -3 1/2 into here, -3 1/2 into here makes this part become a negative, and this part become a negative. A negative times a negative gives me a positive. Since I only care about the plus minus of the answer and not the actual answer, the negative times a negative giving me a positive is really easy to plug into that number line. So it's not as bad as it looks. All right, so now we've tested our endpoints. We've tested our points that are in between these intervals. And now, why did I do that? Here's why. Let me rearrange this a little better. Okay. If I have a plus sign in my first derivative number line, what that's saying is my first derivative is positive, which means the slope of my function was positive, or my function's going upwards, increasing. So there it's going uphill. Where my first derivative is negative over a region, my original function is going downhill. and then uphill again. So although this is a first derivative number line, this blue sketch that you see is just an idea of what f of x is doing. So what I've done now is I have a primitive idea of where maximums and minimums might occur. And I also know where my function f of x is increasing and decreasing and increasing. So by filling out my first derivative number line, I have good insight onto what my graph of function f of x looks like. Before we move on, I have a danger point to show you. You notice here that my test points revealed a plus, minus, plus. And that's a nice alternating pattern. It's so nice, and humans love patterns, that you're going to believe that you always follow alternating patterns when you fill this out. But that is definitely not true. So don't get into that habit, because the AP test writers like to find out the students that are in that habit. You will come across some number lines that might go something like this: plus, plus, minus, plus, minus, minus. I mean, you just don't know what that pattern is going to be, but it's a big danger to assume that it's going to alternate, because although it does a lot of times, it doesn't have to all the time. Okay, I'm continuing on with that number line, but you see I have some mumbo jumbo here. So earlier I said that to get full credit for your calculus knowledge, you have to make sure that you justify in the AP style. So when they ask you questions, you need to give them a justification for your answer. So for example, if they said, is function f of x increasing or decreasing at x equals 3, and x equals 3 is right here, you would say f of x is increasing because my first derivative is greater than 0. The part I'm going to underline in red is the AP justification. All right, so you get the idea. Here's a decreasing region. There's my AP style justification. Many times they won't give you credit if you don't have that justification. So here we see there's a maximum. Here's their justification, because the first derivative switches from plus to minus. That's fancy talk for saying my function's going uphill, la da 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 da, and then it's going downhill, la da 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 da. You can't help but have a maximum if you go from positive slope to negative slope. If I go from negative slope to positive slope, I've got a minimum. Negative slope to positive slope, minimum. Now a couple of weird things. At x equals negative 4, I have a minimum, but you can't say because the slope f prime of x switches from negative to positive, because there's no switching there. So you have to do this thing. The first derivative is positive to the right of that endpoint. And as I mentioned earlier, at x equals 5, there's no maximum or minimum. So these justifications are a bit clunky, but you have to get used to them, because very frequently you would not get credit, even if you had the right x value, if you don't have the right justification. So I've gone back to the very first page of these notes, and at this point, what we've found out is some mystery function that we don't even know what it looks like. We now know how to find the critical values because they go into the first derivative number line. And once we do our first derivative number line, we can get increasing, decreasing, and maximums and minimums. So all of these three have to do with the first derivative. These next two have to do with the second derivative, so we're now going to build a second derivative number line. The The good thing about building the second derivative number line, it is not much different at all than what you were doing when you built your first derivative number line. So pitter patter, let's get at her. Here's my original function we've been working with. Here's my first derivative. We've worked with that for a while, but now we move on to the second derivative. And we're going to do the same thing we did when we built the first derivative number line. I'm going to ask myself, when does my second derivative equal 0? When does my second derivative become undefined? And whatever x values I come up with, they're going to go on the number line. Well, let's see, I want to keep some of this secret from you. That'll do it. All right, so when does that thing equal 0? At x equals -1/2. When is that thing undefined? Well, 2x plus 1 is very well behaved. There's no corner points, there's no discontinuities, no jump discontinuities, nothing. So it's never undefined. Don't get lulled into a false sense of security and skip this, because this will come up. So now, as soon as I have that, I put that on my number line. I'm going to go faster now. Here's my second derivative number line, the endpoints that they told us about when we started the problem. This value goes there. This is technically not called a critical value because critical values only go with the first derivative number line, but it acts like a critical value. And now within this interval, I take any number I think is easy to work with and plug it into the second derivative. Same thing here. So I get a negative, which means any number in here would have given me a negative. Any number in here would have given me a positive. Don't assume that they will always alternate, because they won't always alternate. And now I can, from this exercise, come up with curvature conclusions. My function is concave down at x equals -3. Here's the AP style justification. More AP style justification. And the point of inflection, which is what I told you before at the beginning of the video, which means you probably forgot by now because that was a while ago. Anytime a function is going from a concave down and switches into concave up, like what happened here, we have a point of inflection. The same thing would happen if something was concave up and then switched into concave down. We have a point of inflection. And that is because f double prime of x switches sign. This is the justification for a point of inflection. I won't say what people mistakenly write, because then I'll plant it into your mind. But if you write something other than that, you're going to think that you're correct, and you're not, because there'll be a loophole in what you write. This is the correct justification for a point of inflection. And by the way, all of these things that we got by doing the second derivative number line that you can barely see up there any longer, these things make sense with that sketch that I showed you at the beginning, which we secretly wouldn't, or we really wouldn't have, it's just a secret. But we have a concave down area. We have a concave up region. And where the concave down turned into concave up, we had the point of inflection. Okay, we're close to darn done, but I want to point out some things for your benefit. Let's revisit critical values, which I told you the definition was first derivative equals 0, first derivative undefined. And I warned you that it was really easy to skip this thing because so often it leads to nothing of substance in the problem. But don't skip it. I'm going to show you an example of why that would be the case. Sometimes an AP example will give you an unknown function, so I'm not going to write down what it is, but then they'll give you the derivative That is the result of that function. So some mystery function leads to this derivative. And then they'll ask you questions about the maximum or minimum or concavity of this thing. Well, let's pretend we were asked about maximum, minimum, increasing or decreasing. We would need a first derivative number line. And one of the first things you think about on a first derivative number line is what are the critical values. So I can put those on the number line along with the endpoints. Well, if I needed critical values, I would say, when does my first derivative equal 0? When does my first derivative become undefined? And I would literally write these things out on my paper to help focus myself. And then, although this derivative looked like it was going to be terrible, because my gosh, it's a fraction with trig and all that stuff, it's not nearly as bad as you think. When does a fraction equal 0? When its numerator equals 0. For example, 0 over 8 equals 0. 0 over 17 equals 0. So when the numerator equals 0, my first derivative equals 0. And if I solve that, that's x equals 2, makes this first derivative become a 0. All right? When is a fraction undefined? You remember that from good old pre-algebra. 8 divided by 0, explosion. 17 divided by 0, explosion. So this first derivative is undefined when the denominator is equal to 0. So I just set the denominator equal to 0, and I solve, and I get these two trig values, or unit circle famous values. Critical value, critical value, critical value. I go ahead and I put those on my number line. I'm really cruising fast now through here. Here's my first derivative number line. I should label it my first derivative. Endpoint, endpoint, critical value, critical value, critical value. This looks like a mess. And I'm not going to fill out the rest of it, but just for an example, if I wanted to figure out the plus or minus in here, I pick an easy value to work with. I like pi over 2. It falls in between here. And if I take pi over 2 and plug it into my derivative, it's 2x minus 4 over sine of x minus 1/2. That's the original derivative, first derivative. And now I can figure this out. This is pi minus 4. Now at first I say I can't figure that out, but remember we only need pluses and minuses in here. So pi is a little bit more than 3. 3 minus 4 is a negative number. This one I can do because sine of pi over 2 is 1. That's a 1/2, but really I only care that it's a positive number. A negative divided by a positive is a negative, and that's how I know to put a negative in there. I can do something similar in here and here and here if I feel like it, but we're all getting tired, aren't we? So this example was to show you that don't skip this because it can happen, and when it comes time to filling out your number line, realize that you only need pluses and minuses. So you can plug into a first derivative and it's not nearly as bad as it might have looked. And finally, the last thing I'm going to do is just remind you that you have to justify your results AP style, which means you always have to refer to the first derivative or the second derivative. So I'm just going to unveil some more examples of justifying. They don't come from any specific problem, so you're just looking at the style of my answer. There's no math to back it up. So you may need to pause the video if you want to digest this more. I'm not going to hold it for too long. Here's how I would justify increasing and decreasing. Pause it if you need more time. maximums and minimums. First derivative is switching. Also, for maximums and minimums, we have the issue of endpoints. So, for example, if there was a maximum at a right endpoint, or if there were a minimum, it takes some thinking to put the proper logic down on paper, because if I had a maximum over here, I would say max because okay. And finally, the curvature ones. If I'm looking at concavity, that's a second derivative issue. And a point of inflection is where we're connecting concavities. So that is also a second derivative issue. Okay, that's a ton of information that we've had, but realize that this is literally an entire chapter in a lot of calculus textbooks. There's 2 add-on videos to this. They're much shorter, so don't worry about it. And you don't need those add-on videos right now. They will come later on after you've done some practice with this stuff. Thanks for hanging in there if you're still alive.